All right, hey everybody, we're here on slideshow 17. These are predicate derivations and doing some example of universal out arguments on pages 15 and 16. So the first one we're going to do has three premises. So I'll go ahead and write those down just as we did before. So for all x, if hx, then fx. Premise 2, for all x, if fx, then cx. And premise 3, ht, which says that individual t has property h. Make sure you can see this here. So we denote those are premises, and then we're going to try to show that ct. So here's the rough idea. We know that t has property h. We know that all h's have property f and all f's have property c, so therefore t must have property c, and we just need to somehow demonstrate that. So that's what we're going to try to do here. Okay. The first step then is to get rid of these quantifiers. So take line 1 here. If we know that every h is an f, then we know that if t is an h, then t is an f. And that follows from our universal out rule. So that follows from line 1 by universal out. Now notice we could have replaced the x with any constant we wanted. It could have been a, b, c, whatever. We did t because that's going to be useful, because now with 3 and 5 we can do arrow out to get ft. And that comes from just our old sentential rule, arrow out. What next? Well, we're trying to get to ct. We're not quite there, but we look at line 2 and we see, oh, well, if all f's are c, then that applies to t also. So if ft, then ct, that comes from line 2 by universal out. Again, we could have done any letter there, but we decided to do t because it's useful. And then, again, from arrow out, we get ct. That comes from 6 and 7 by arrow out. And so that's it for our proof. We just have to now finish it up. This is a direct derivation. And we cancel and box. All right, let's try the next practice problem. I'll write down the premises first here. So premise 1 is for all x, fx, and tx. This says that everything is both f and t. Premise 2 says if fb and TL, then everything is h. And we want to try to show that HC. Okay, how are we going to proceed? Well, first we're going to need to show that FB and TL, and then we can use arrow out to get that everything is h, and then once we know everything is h, we know that C is h. So how do we get FB? Well, it's tempting here to do universal out here with line 1 and make this x a b and this x an L. But we're not allowed to do that. We have to make the x's the same in any one application. So we have to go through a kind of annoying step. First, we can do this. FB and TB, that follows from line 1 by universal out. And then we can do the same thing with L, also from line 1 by universal out. Now we can break apart the parts we need, in particular FB here and TL here. So we'll first take FB apart. That comes from line 4 by and out. In line 5, we're going to take the other half, TL, from line 5 also by and out. Now we can put 6 and 7 together with and in. Oops. That should be FB and TL from 6 and 7 by and in. Okay. Why is that useful? Well, now with line 2, we can do arrow out. So line 9 gives us that everything is h. That's from line 2 and 8 by arrow out. And we finally finish up the proof by saying, well, if everything is h, then we know that it applies to C as well. So C is h. That comes from line 9 by universal out. So there we've shown what we set out to show, and it's a direct derivation again because what we set out to show is at the bottom of our proof, so we cancel and we box. All right, let's just do two more examples, the final two examples on page 16, I believe, of the slideshow. First, I've got to switch my paper here, so just bear with me. All right. Got it lined up here. There we go. Okay, so for this example, the third example, we've got a couple of premises. So for all x and all y, Lxy. Then we've got premise 2 for all x, if Lxx, so if x bears the L relation to itself, then Ex. And we're going to try to show that EB and LJB. So make sure you can see these here. So that's our premise and our premise, and we leave that blank so we're not sure exactly how the proof is going to proceed. Okay, so how should we do this? Well, we should try to get each part independently. So let's first get LJB because that's the most obvious. So we're going to go to line 1 here. Line 1 says every x and every y bears the L relation to each other. So we're going to want to turn this x into a j and this y into a b so that we get this. To do that, we just have to do things in the right order. First, we take off the first quantifier, universal y, L, and then we need to make sure we replace the x with the right letter. We want the j to be first. So we're going to replace that x with a j. And so we get this from line 1 by universal out. Now we can take off the universal y quantifier from line 4 to get L, J, B. And that comes from line 4 now by universal out. Okay, so we've got half what we need. Now we need to figure out how to get EB. Well, the obvious place to get it is from line 2. So let's do universal out to make that x into a b. That's going to give us if L, B, B, then EB. That comes from line 2 by universal out. Now we just have to figure out how to get L, B, B. And the trick here is to go back to line 1, because remember we can make this x and this y anything at all we want. So let's make them both b's this time. That is, let's start by taking off the universal x quantifier and replacing the x with a b this time. That comes from 1 by universal out. And then we're going to take the universal y quantifier off and replace it with a b again, just as we did last time. To get L, B, B, that comes from line 7 by universal out. Now we just have to put our parts together. We've got, oh sorry, not quite yet. Now we need to do arrow out. LBB, arrow EB, and LBB gives us EB. That comes from 6 and 8 by arrow out. Now we can put things together. So we've got EB and we have LJB, so we can put them together with an and to get EB and LJB. That comes from lines 5 and 9 by and in. And now our derivation's complete. It's a direct derivation, so we cancel and we box. And just one thing worth pointing out, notice what we see here when we look at lines 4 and 7. That shows that you can go back to a premise you've already used and reapply a rule in a slightly different way. In this case, we transformed the x into a j in line 4, and then went back to line 1 and transformed the x to a b in line 7. That's perfectly fine. It's perfectly allowed by the rules. Last example, before we learn a new rule. Our premises are going to be not hj or something as m, and nothing is m. And we want to then show that not everything is h. And the key thing to remember here, or recall, I guess, from our sentential derivations, is that we still have all of our proof techniques, all of our derivation techniques. And this is a great chance, in this case, to do an indirect derivation. So in an indirect derivation, recall, we get to assume the opposite. So we're going to assume that everything is h and try to show that that leads to a contradiction. How should we proceed here? Well, notice 1 and 2. That's a perfect form for or out. So we can derive not hj. Since we know that this is false, we know that this must be true. So we get not hj from 1 and 2 by or out. Okay? What do we do now? Well, we're looking for a contradiction, and look at line 4. We know that every x is h from line 4, but we know that j is not h from line 6. So if we just do universal out with line 4, we should be able to get a contradiction. That is, we take off the quantifier and replace x with anything we want. Let's choose j. That comes from line 4 by universal out. But that's a contradiction. hj and not hj. 6 and 7 by contradiction in. And so we've directly derived a contradiction, which means we've indirectly derived our conclusion that says that not everything is h. All right, that's it for these examples. In the next video, we'll introduce a new rule.